Okay, so thanks the organizers for keeping this wonderful meeting alive. So it's a very challenging thing, I realized, for umpteenth time to say things in 10 minutes. So this is the failed attempt I have been trying for last a couple of days. So the idea is emergent stability of local quantum matter under high fields and couplings. So the emergent word is not in the sense of quantum field theory where you see emergent phenomena and when you project things in lower energy manifolds. It's a different kind of things we'll describe this. So these are the references. So this is in red because it's a review which probably summarizes everything. And most of these works were actually not only done but also initiated in the rather intellectual level by this first author of this paper, Pushmi Haldar, who was my grad student and now at PKS doing postdoc with Rodrish Moishner. Okay, so I'll just try to entice you into a set of results and our thoughts on that, and so that you can just probably think about it a little bit and things can probably progress. So the idea is, so if you have Gibbs statistical mechanics, so what it is basically is entropy maximization subject to local conservation laws. So you respect the local conservation laws and maximize the entropy, then that gives you your distribution function, which is the Gibbsian distribution functions. These lambda k's are the Lagrange multipliers like temperature. The IK's are the additive local conserved quantities, and that's how statistical mechanics work. If you go to quantum mechanics, then an operator which commutes with the Hamiltonian is conserved. So there are conserved quantities in quantum mechanics. If you come to quantum mechanics tells these are the operators which are conserved. And if it doesn't, then they are not conserved. So if you want to go from quantum mechanics to statistical mechanics, then we have to go to some hypothesis. This eigenstate thermalization hypothesis or quantum chaos or some sort of that, some equivalent of that in various versions for many body systems. And then you go to these things where the only constraint in your system you assume are the exact conservation laws. There is no other kinds of constraints. So what we will try to say here that there can be other constraints which are not exact conservation laws and they can substantially affect these distributions. And probably this sort of distributions, this sort of principles of maximizing the entropy subject to the exact conservation laws are not sufficient. So for example, what if there is a Hamiltonian which has a large part and a small part? And the large part actually commutes with the Hamiltonian, doesn't commute with the Hamiltonian exactly, but there is a small, it's a small number. It's number, and of course there is an operator there. I just wrote the order of it. And if this is small enough up to some value, is there a threshold or something so that the things are still conserved when epsilon is small enough? This is the sort of question we will trying to prove. So in general, the answer is not known because there is no threshold theorem like KAM theorem, KAM theorem in quantum mechanics. This is Kolmogorov-Arnold-Moser theorem we have in classical mechanics. There is none of them in quantum mechanics. The general belief is basically every conservation is destroyed if you have an infinitesimal amount of thing that breaks the conservation law. So if this commutator is infinitesimally small, it's sufficient to break the conservation laws. So we ask this question in a more general setting, a setting where we kill also the energy conservation minimally. So we have a interacting many-body system which doesn't a priori has any local conservation law. Plus we put a unitary periodic drive. We drive a Hamiltonian with time, so energy is no more conserved. Typically, this Hamiltonian should not commute with itself at various times. That makes the problem complex, and all the trivial results which can be mapped to the time-independent problems are gone. The question is what happens then? So if you just have extrapolated the idea here that you maximize the entropy, then you get an infinite temperature state because there is no conservation law at all, not even energy, nothing. So it spreads over the entire Hilbert space almost uniformly, and it looks like an infinite temperature if it look locally. So with that, we come to the summary of the talk because I at least want to give the summary at the beginning, and then I'll come to the results which illustrates the summary. So first we show that under very strong drive, actually non-integrable quantum system, interacting quantum system, which are generic, may not thermalize to locally infinite temperature like scenario. And why it doesn't is because there are approximate but perpetually stable conservation laws, which appears due to the drive, which were not present in the undriven system. It happens due to a massive scale of destructive quantum interference. And this happens there beyond the threshold of the drive strength. So if the drive strength is beyond the threshold, then only this happens. So this threshold phenomena appears here, like as it's a reminiscent of the camp scenario, not exactly the same thing formally, but they're reminiscent of the phenomenology. And we found analytical signature of this kind of phenomena, this threshold phenomena beyond which things and conservation emerges in a very enormously large class of spin systems, the Ising model of any kind, in any dimension, any form of Ising interactions, and any two-body Heisenberg interactions in any dimension, anisotropy and bond distributions. It's pretty much covered every condensed matter systems we work with. Okay, so that's why the summary first. So, okay, if we take a horrible model which has no symmetry, we break the translational symmetry at the boundary, we drive the H term, this is the drive term, which is a square pulse, signum of sine omega t. And then what we get is here. So for smaller drive amplitudes, it immediately thermalizes, goes to 0. As you increase the drive term, size of the drive term, it goes to 0 more slowly. There is a threshold, you'll see in the next slide, after which it suddenly completely freezes to its initial state. And this happens, this threshold does not move with system size. If you see here a log plot, you will see it becomes sharper and sharper. And here, it doesn't increase, actually freezes more with increasing system size. So you see there is a crossing. So this guy goes down with system size, this guy goes up with system size, so there is a crossing. So it doesn't move, but they crosses over somewhere. So there is a finite value of this, where the threshold takes place. And if you plot with omega, then there are some peak value structures which you can find. It's a very simple criteria. At this peak, the systems are completely frozen. So we have taken two kinds of initial state. One is 0 temperature, one is very high temperature, beta 10 to the minus 2j. And we see for both of the things, these things are same. So we are plotting the infinite time limit of the dynamics divided by initial values. So basically, we are saying this freezing is perpetual. So we did various other kinds of models. So it's a nearest neighbor Ising spin. This is 3 spin interactions. This is a long-range model, Heisenberg model with isotropy and anisotropies of various kinds. So all of them shows the same phenomenology. So okay, with this we come to the basically the last slide. So previously we were doing infinite time limit of a finite size system. We could do that by calculating the diagonal ensemble average, do the exact diagonalization of the whole system, whole spectrum. Here we are doing infinite size system, but for finite times. The interesting thing is this was done with Frank Polman and Alexander Witek, and Ushmi proposed this also again. So initially it was believed it's not doable because this kind of DMRG type of algorithm, just after 4 or 5 cycles, it just exhausts your memory. But a very interesting happens here actually. Beyond the threshold, below the threshold, just 4 or 5 cycles you can go. But beyond the threshold, you can go for hundreds and thousands of cycles. Currently it is 10 to the power 4 or 5 cycles we have gone, and we have not exhausted yet, and the computer time just goes away. And you can drive it for thousands and hundreds and thousands of cycles without increasing the entanglement of an infinite system. So this is work in progress. So if you want to really want the L going to limit and T going to limit, that's also exists, but it was shown in the integrable systems, which was done in 2010. We see the same peak value structures, same kind of freezing. Here, in addition, so from a later work, we know that there are n number of periodically conserved quantities that exhausts all the exact conserved quantities, but that doesn't sufficiently describe the ensemble actually. We have to take into account that extra emergent conserved quantity which we saw earlier in this paper. And this is at L going to infinity and T going to infinity limit. So with this we come to what we didn't discuss. We had a lot of analytical treatments of these things, a lot of maths we skipped. So those are basically some kind of expansions. And these kind of expansions have two things, important things about them. There are resonances, which we didn't discuss, and actually we can capture all the first order resonances just few seconds. First order resonance captures all the real numerical resonances, which strongly suggests that the series is asymptotic, and maybe there is an underlying analytical function which this divergent series actually represents, which is this point. And this is similar to the stability of solar system beyond Cam threshold. So I had a brief discussion regarding this with Arnold in 2010 when I picked up this topic with him. He said this can be stable because of some unknown reason which mathematicians do not understand, but there is a vast majority beyond where series are actually convergent. And there are further constraints, just not one conservation law, which we are looking into. Okay, thank you very much for your attention.
So one question was, do you think this is kind of stable if you add a little bit of dissipation? These results,
dissipation probably they should show some resilience, but I don't think it will be stable, completely stable. Dissipation in the sense, if you the question is how you treat the dissipation. So if you take a little bit of system in a bath, so what locally, that's what we are doing actually.
No, right now you don't have any dissipation, right?
Now, if you look at a subsystem, then to the rest of the system we have.
Like real dissipation, like
Lindblad is
like
not.
why even at one side.
Yeah, that is the question. We had a discussion with Thomas Person regarding that, whether Lindblads are the real dissipators or looking at the subsystem of a whole system is the real dissipation. Lindblad is quite artificial because you put a red by hand and you say this film must flip with this red. And if you impose that, then of course there is not much chance that it will survive because you're asking him to flip anyway at a given rate. So as far as I understand, if you really employ Lindblad, there are large timescales, but they eventually goes down, they go down. It's for closed systems. But if you think of a subsystem of this guy as a system and the rest as a bath, then of course, as you can see, it dissipates, it has a so you have to have the bath really under the drive. If you don't drive the bath, probably.
Yeah, if you don't drive
the bath, then it loses it.
One question. So the emergent conserved quantities, are they local or they completely involve all the sites of the system?
They are global conserved quantities. It's a very good question. It's a local operator, but it's a global conserved quantity.
So if you think of a subsystem, then a quantity just of that subsystem is that's not necessarily conserved.
That's actually true. Yes.
Okay.
Right.
So can you somehow decrease the threshold? Like if you put some disorder or something?
Actually, disorder hinders this process. If you put, so it depends on which direction you put disorder. Suppose you put the disorder in the z direction, then actually the things become worse. So, but if you put disorder in the x direction, then things stabilizes a little bit more. Yeah. So whether this changes the threshold or actually stabilize an MBL phase is something we are working. Oshmi and I am working with Vedika. So far the understanding is there are certain ways you can map the static problem to a Floquet problem by Schiffer-Wolff kind of stuff, and then you can get certain stability analysis of this kind in the rotating frame, and that shows actually you can probably stabilize MBL by this kind of things. But interesting thing, this threshold is still between 10 and 18 even for infinite system. So as you were worried, probably for 20 size, 18 is a very large threshold.
Yeah, I was thinking if you start in the thermal side of the MBL and then try to do this, will the threshold become small?
Threshold doesn't depend on the initial state. As I showed, we did a.
No, not the phase, the parameters of the model you choose in the thermal side.
Right.
Then
Okay.
Can you decrease the threshold?
We don't know the answer to this question. We are just trying to probe this sort of questions. It's a very nice question. Okay.
Thank you, speaker. So